Welcome to HC32. Keynote 2, AI Research at Scale, Opportunities on the Road Ahead.
So I'm happy to introduce Dan Belov, who is my colleague at Alphabet and a distinguished engineer at DeepMind. Dan has his own bio as part of the talk he's going to give, so I thought rather than doing the traditional bio, I would offer some views on what I think is great about him. Dan is a system builder in what I would call the classic Google style. He always questions basic assumptions and is willing to rebuild the world in unconventional ways to solve the problem at hand. I think this approach has led to some surprising solutions like corkboard servers and containerized racks to modern data centers as we see them, and most recently perhaps to TPUs. From the architect's perspective, I don't know whether Dan has ever read Hennessy and Patterson, but he seems to live and breathe the quantitative approach. He demands that we pick and use the right metrics and optimize appropriately for them in our work every day at Google. And Dan, when you meet him, will be incredibly modest and humble. He'll claim to just be a systems person, but I should warn you, he has this unnerving ability to jump into a new field and rapidly figure out what's important about it and then put the connections back together across fields, whether it's neurobiology or domain-specific accelerators. I think his talk is a really great bridge between the forefront of artificial intelligence and DeepMind's own quest for artificial general intelligence and the machine building that we do here at Hot Chips. He will tell us about the theory, and he'll tell us about how the theory and the algorithms and the code distill into hardware. But I think the coolest thing to watch for in his talk is the intuition behind why a given technique is important. So with that, Dan, please take it away.
Hello, everyone. Really glad to be here. Thanks, Cliff, for inviting me to give a talk and to participate in this wonderful community. I want to tell you today a bit about my experience with AI research on massive scale and what opportunities I see on the road ahead. So first, I wanted to mention that I have no formal training as a machine learning researcher nor a hardware engineer. I'm simply a software systems engineer, so my views are going to be heavily colored by what I find exciting from that perspective. In a way, my life story is about working with increasingly bigger and more powerful computer systems. I was born in Estonia during USSR, and my first experience with computer came when I got a Commodore VIC-20. It had a broken tape interface, so the only thing I had to play with was the BASIC interpreter. Through some luck, I eventually went to Carnegie Mellon, where I got to play with some big SGI machines, and then spent 4 years at Panasys, where we built massive distributed file systems. In 2005, I joined Google and spent 11 years working on increasingly bigger distributed systems that handled all of the public and private data. Then in 2016, I got a really exciting chance to join DeepMind, and for the past 4 years, I've been building up the engineering teams, compute, and robotics infrastructure there since then. One of the central themes in this talk is sort of about my desire to keep building ever bigger and bigger machines. So in this talk, I'd like to take you through an introduction to DeepMind and what we do, then give a brief intro to reinforcement learning, then look at some examples like batch learning for robotics, AlphaZero, and graph networks for simulations. There will be pretty videos there, but if you already know all the stuff, I will see you at around 25th minute mark. We'll then look at the gap between demand and supply for compute and discuss 3 opportunities for the future that I find interesting, and I hope they would stimulate a good discussion in the community here. So, DeepMind was founded in 2010 by Demis, Shane, and Mustafa to solve intelligence. It's like an Apollo program, but for artificial general intelligence. DeepMind is a research institute within Alphabet that is now about 400 research scientists and growing. Our research setup is unique in the sense that while we have the backing and resources of a giant company, we operate completely independently, have very long-term goals, and are free to focus on fundamental research into artificial intelligence. What really matters to me, however, is the second part of our mission. We'd like to use AGI and the powerful tools we build in the process of getting to it to solve many open and important problems in the world. So, DeepMind has a unique approach which is inspired by neuroscience. This does not mean that we're trying to exactly implement artificial structures that match what we discover in the brain. Instead, we believe that neuroscience can act as a catalyst for the ideas that drive the field of AI forward. Conversely, there is also a growing body of AI research that feeds back into neuroscience and helps us understand neurophysiological phenomena such as the firing properties of dopamine neurons in mammalian basal ganglia. I recommend you read this paper by Demis to really get a flavor of this kind of neuroscience-inspired research that we do. So we do a lot of research by using games. Games have clear objective, we can quantify performance against the human level, we can efficiently test new approaches in parallel simulations. They can act as a simplified microcosm of the real world, and of course, in cases where we need higher fidelity, we also use physically accurate simulations. If we want systems that can form plans, navigate the world around us, make sense of sensory input, make decisions to achieve long-term objectives, understand language, and cooperate with us, these are skills that various kinds of games require to master. So, the first time I heard anything about DeepMind was when I saw this video in 2014. The only thing the agent sees here are pixels and the score. And the only things the agent can do here is to go left or right. The games themselves are thousands of steps long, and you can see the agent gradually learn how to make better and better decisions until finally it figures out a strategy that is extremely human-like. Here it comes. It's basically minimum effort for maximum gain. A lot of our research is about building such agents that make decisions towards some goal. And what is fascinating to me is how human-like some of the solutions we see them discover are. Of course, we can now solve a lot more complicated tasks. Here's an agent called R2D3 from 2019 that is solving puzzles in a 3D world. Each step in this sequence must be completed in order and must be implemented by the agents as a sequence of low-level actions, as if the agent had a game controller in its virtual hands. The necessity of completing such a long sequence of high-level steps makes it unlikely that the task will ever be solved by random exploration. And so note that each step involves interaction with a physical object in the environment, shown in bold. Here you can see the agent perform these actions. R2D3 can perform human level or better on this task. Honestly, over the years of watching these agents, it has become harder and harder to tell apart whether it's human or agent playing. So how is this possible? How are our agents able to make thousands of decisions to reach distant and non-obvious goals? Modern machine learning methods like deep learning give us a way to infer knowledge about the world from observations. Machine learning also studies how to guide observation to gain new knowledge through discovery and exploration, which is a crucial point that we'll discuss later. And finally, machine learning is also concerned with how to build systems that synthesize existing knowledge to create something new. From a practical perspective, we have recipes now to train programs to perform desired functions and generalize to previously unseen inputs. So the magic of machine learning training comes from a recipe with 3 ingredients. First, we need the largest possible network with fewest built-in assumptions. Second, we need a lot of clean data and a clearly defined objective. And of course, third, we need lots and lots of compute. With supervised deep learning, we can now learn pretty much any program from observations to desired outputs, subject to there being enough data and compute. These programs are able to generalize and work for inputs that were never seen during training, as long as they are reasonably similar to what was seen from the training data. More is truly more in this case. More diverse data, more compute, and bigger networks give better results. Generally speaking, we see networks grow maybe 3 times bigger every year on average. At DeepMind, a lot of our research uses reinforcement learning, which has roots both in dynamic programming as well as in neuroscience. In reinforcement learning, we have an agent that performs actions in an environment and observes their effects in relation to some goal. Reinforcement learning is a study of what decisions we need to make today, such that they would be consistent with all of the decisions we most likely will have to make in the future. Here we have an agent that uses a policy pi to select an action A at time t, and then observes new information O and reward R from environment at time t plus 1. The goal is usually to maximize total reward seen during the lifetime of the agent. So the policy is the program that makes the decisions of which actions to take. Deep neural networks are used in the agents to reduce the need to memorize what is the best action to do in a state by utilizing their ability to generalize to previously unseen inputs. When controlling a car with an RL agent, instead of looking up whether to go left or right, giving the current camera view, we can train a neural network to generalize from prior observations and output such actions instead. Another critical thing to know about reinforcement learning is the concept of a value. Value function is a sum of all possible rewards from the environment that an agent can achieve from now until eternity. So for math to be nicer, as well as how things are usually in the real world, we'd like the total reward not to be infinite. So we add a discount factor that causes the future rewards to exponentially decay. This allows us to create function fixed points, and now the values at different states of the world give us information on how advantageous these states are with respect to maximizing our goal. A value of a car in a ditch is small. The only way out is to get towed to a repair shop. A value of a car driving safely on a motorway towards the destination city is large, as all likely future states will bring the car closer to its destination. Of course, just like with policies, we use deep neural networks to learn value functions. One nice thing about the fixed point formulation is that it gives us a recipe to train such networks against future values of themselves. Let's look at some examples, like DataDriven Robotics. By harnessing a growing dataset of robot experience, we can learn control policies for a diverse and increasing set of related manipulation tasks. To make this possible, we also introduce reward sketching, an effective way of eliciting human preferences to learn the reward function for a new task. This reward function is then used retrospectively to annotate all historical data, which was collected for different tasks, with predicted rewards for the new task. The resulting massive annotated dataset can then be used to learn manipulation policies with batch reinforcement learning from visual input in a completely offline way. So in other words, without any interactions with the real robot. This approach makes it possible to scale up reinforcement learning in robotics, as we no longer need to run the robot for each step of learning. So the maxim is never throw any data away, no matter how bad it is. It's true at Google, and it's also true for machine learning, especially in robotics. We start by pooling never-ending dataset of robot experience. This dataset contains everything our robots have seen in a robotics lab over their lifetime. A lot of the data is garbage. Real world is a notoriously difficult environment. Things break, props fly out of robotic cells, and humans interfere for their amusement. We do, however, try to bootstrap the dataset with as much good data as possible. For that, we use human operators to demonstrate actions that work. Here's Sirkin was operating the Sawyer robotic arm to stack objects in our robotic cells. Humans then watch some videos and annotate them with rewards. We make sure to annotate both good demonstrations as well as videos that have nothing to do with the task. Given a task, we have a browser-based interface that allows a human to sketch how much reward the robot should be getting as it's trying to accomplish a task. Some of these tasks to annotate would come from human demonstrations, and some would come from random policies or previous experiments. A good diversity of data is crucial here. This circumvents one of the hardest problems of reinforcement learning, the chicken and egg between learning good policies and specifying rewards. So for many hard tasks such as, say, protein folding or robotics, it is very difficult to decide how well the agent is doing with respect to the goal. While we know when a board game is won or lost eventually, real-world tasks give us no such luxury. So we have to try to learn programs that assign rewards from observations. Human-specified reward sketches are next best thing, and we can train neural networks to mimic decisions humans make. We take the trained reward function and annotate all existing videos in the never-ending storage with new rewards. Now that we have a fully annotated dataset, we can proceed with learning better policies and value functions to solve these tasks. Training in this case looks very much like supervised training for deep neural networks. We have the annotated data, and we can optimize the policy and value functions to match the recurrent relationships that would fit it. Finally, we can take the trained policies and run them on real robots for evaluation. Of course, as usual, everything that is executed on a robot is once again stored back into never-ending storage. So this allows us to create a virtuous cycle where we learn better and better policies on each iteration. Better policies create better data, which in turn allows us to create better reward annotations, which in turn improve learned reward annotators, which then improve the quality of the overall dataset, which can then be used to train better policies. Of course, this does not strictly have to be a pipeline of iterations. Instead, all of the phases proceed in parallel. As a result, we see pretty amazing behavior. This robot is really keen on stacking and does not let human interference deter it. I should also mention that to train such robust policies, it is essential that we train on not just nice, clean, perfect examples, but also on lots of bad data. Data where robots do random things and where we can observe failure. Just like children, understanding failure is critical to be able to learn good behavior. We also see our agents outperform humans in how fast they can do the tasks. And finally, we even see generalization to never-before-seen objects. Methods such as batch RL with reward sketching leverage scaling up compute by iteratively improving the quality of the datasets we already have, while only adding new data to them in small increments. This is crucial for environments that are expensive to perform in, like robotics. This kind of iterative improvement in dataset quality is one of the attributes of reinforcement learning, because there is an inherent loop between policy exploration and exploitation, in other words, generating new data, and policy optimization. Our research pushes agents to generate better and more diverse data, which they can then use to improve themselves. Another example that is interesting to look at are the connections between search and models of environments. So let's look at an example of how reinforcement learning works in our agents that play Go. Ancient game of Go is played by 40 million people worldwide. It is one of the simplest games in terms of structure, and also one of the most complex games in terms of number of positions, and had been one of the grand challenges for AI. Here is Demis and Lisa Dahl accepting an honorary ninth Dan title for AlphaGo after a historic win in 2016. Here's a representation of a search tree of moves in the game of Go. Brute force search of the game moves is not tractable because search space is simply enormous. Also, historically, it has been very difficult to write programs to decide who is winning based on a board configuration. The goal of the game, of course, is to win. Our agents train a deep neural network that assigns a value to each board position that represents the likelihood of winning for the player. The beauty of reinforcement learning comes from the fact that there is a relationship between values of a state of the world now and the value of a state of the world later. This means that the value of a state now has in it all possible discounted values of the states we can get to in the future. Trivially, if the board is full of black stones, we know that possible games are likely to lead to our win, no matter what white stones are placed, so the value of such a board would be high from the perspective of the black and low from the perspective of the white. The value of a state can tell us if we want to explore a branch in the search tree. If the network predicts a low value for a node, we know that we don't need to explore any children of it. Most likely, any outcomes will lead to our loss anyways. This means that the value networks allow us to prune the depth of our brute force search. We also train a policy network that is used to pick which moves to make. Just like the value net, policy network is also a deep network and is trained in a supervised manner from data of played games. The policy network learns to produce good moves so we can reduce the breadth of the search tree by picking only the best moves. Notice that there are recursive relationships between the outputs of value and policy networks at different levels of the tree. Reinforcement learning teaches us how to use such relationships to create better training regimes for deep neural networks than just learning blindly from data. In combination, choosing only good moves and not going down paths that are likely to lead to a loss allows us to prune the intractably large search space. Of course, these techniques are not just limited to Go. While AlphaGo used human games to bootstrap its value and policy networks, AlphaZero algorithm was able to achieve superhuman performance in chess, shogi, and Go by training purely against itself, using a game simulator with zero human knowledge injected beforehand. The fewer assumptions we use to build our agents, the more general these agents will be. This is a major theme in our research. Replacement of human-engineered features and algorithmic assumptions with more general self-bootstrapping methods. But what happens when the environment we are working against is too slow or too complicated to simulate? Just like we can imagine the steps required for a complex outcome, for example, cooking dinner, our agents also need to be able to imagine the world and the effects of their actions in it, to be able to plan what to do. To do that, we can learn models of the world using deep neural networks and then use them to train a good state value estimators and action policies. In MuZero algorithm, we augment the search to use the model of the world. Instead of searching using a simulator, MuZero can search by feeding its actions in a start state to a model which produces the new state of the world. All of the states in the search tree then are purely imaginary. No simulator required. This allows us to achieve superhuman performance not just in board games, but also in complex visual environments such as like Atari. Of course, Atari is an easy environment to simulate. Many problems that are important for humanity, such as clean energy or drug discovery, operate in environments that are very hard to simulate. Learning correct actions in such an environment is very expensive, so we would like to be able to build models of them that would allow our agents to quickly imagine the effects of the actions they were taking. A lot of research at DeepMind is concerned with the question of how to build such usable models. So, graph neural networks give us a way to model arbitrary systems with least inductive biases. For example, convolutional neural networks and transformers are a variant of graph nets. Here you see a single architecture with a single set of hyperparameters that is able to simulate different material properties. This is a particle-based model, where the particles are modeled as nodes in a graph, and the interactions between the particles are modeled as edges in the graph. The information flows within the graph and is processed using deep neural networks. This is very similar to particle or mesh-based methods in high-fidelity simulations, but instead of, or perhaps in addition to, partial differential equations, we use neural networks. Just like search through game states, graph networks simulate phenomena by iterative computation and regression against their own future, as well as occasional ground truth reference from real-world or existing simulators. Simulations using machine learning models have made tremendous progress in the last couple of years. We are now able to roll out simulations thousands of steps and match physically accurate simulators, with big benefit being able to build both cheaper and more coarse-grained simulations. So all of us obviously know that this work requires huge amount of compute. But why? The simple answer is that scaling up compute works. More search means better results. More iterations of passing information inside a graph network gives us better models of the world. Internal computation like that gives more opportunities to use internal consistency as a training signal as well. This is an important distinction from scaling compute with the size of data. The usefulness of machine learning scales with compute independent of data size. Rich Sutton, one of the fathers of reinforcement learning, has recently reflected on this bitter lesson. We can put a lot of smarts into our algorithms, but general methods that can leverage increasingly large amounts of compute scale better and are easier to use. I'm sure you've all seen these results from our machine learning colleagues at OpenAI. We've made tremendous improvements in algorithmic efficiency over the last 8 years, but it is not nearly enough. During the same time, the computational demand has increased at least 300,000 times. Of course, due to our appetite for solving harder and harder problems and our realization that our methods actually work. Demand for more machine learning compute has increased roughly 10 times a year, while the progress in CPU performance and classical Moore's law has barely budged. And while AI hardware has improved at around 40% per year, we've had to meet the gap by a huge amount of funding. This is clearly not sustainable long term. So these are not Malthusian predictions. There's plenty of economic benefit to machine learning, so funding will continue to grow as machine learning will be used in more and more places. But it might be harder. It might become harder to make fundamental breakthroughs and increase diversity of research if all we have to go on is more funding. We must find a way to bridge the gap. So I would like to now look a bit into the future and talk about 3 opportunities I see for the road ahead and systems for AI research. So first opportunity will come once we stop thinking about chips and instead start thinking about systems. I know the chips are the coolest and most complex and most expensive parts of compute systems we build, and there's a tendency to focus all of our energies on them, but I believe you will find new opportunities if you focus your attention on whole systems. For a research institute, the whole system is vast and is mostly about people. We have hundreds of researchers that run thousands of experiments in a very deep infrastructure stack. Each experiment contains within it a large hyperparameter space that we have to search. All of this leads to an infinite backlog of work. The running joke we have is that when asked, how much compute do you want? We have to answer, all of it. However, deep infrastructure stack creates also many opportunities for waste and bugs. We also have the infinite backlog, but also the infinite backlog and a soft measurement of our overall research progress gives us many opportunities for optimization. While there are parallels, this is a different problem entirely from building an optimal chip for running benchmarks. About 4 years ago, we started a project to optimize this infinite backlog of experiments. It's such a simple idea, really, which I'm sure most of you will recognize. When order does not matter or is weak, then it's easy to build a system to reorder the work scheduled in it to improve basic metrics such as utilization. So, as a result, we doubled the utilization of our compute fleet, all through better packing of experiments. Device utilization, or our ability to actually keep devices doing any work, is a reasonable metric, but the metric we really are interested in maximizing is sustained performance per dollar for the whole research program. How many actual operations do we manage to do versus quoted peak performance? For most optimized research experiments, which are very few due to the large and constant engineering support required, we managed to reach over 70% of flops utilization, which is actually pretty incredible. But if you look at the average, what you see is that the actual utilization is quite a bit worse. This number persists across accelerator types, and while performance in critical production benchmarks goes up over time due to compiler improvements, we don't see this effect across research workloads. How could this be? If anything, it should be easier to optimize research workloads than production systems, as this is a completely closed system. There are no diurnal cycles or anything like that to starve the system of work. In our experience, device peak performance is a pretty weak predictor of the overall system sustained performance. It is true that on average we can assume we'll get 20% utilization from any accelerator, but other parameters seem to be much better predictors of whole system performance. Job startup time, or many memory-bound operations, where of course roofline numbers help. We also often starve our expensive accelerators for data, sometimes due to hardware system choices, and sometimes due to software inefficiencies or configuration errors. Compilers continue to lag latest hardware systems. There can be contention with other jobs anywhere in the system from accelerator to the whole data center fabric. Runtime and Python could have poorly performing interaction, etc. In general, anywhere we look in the deep infrastructure stack, we are likely to have Amdahl's monster look right back at us. So, indeed, the choices of how we run the distributed research experiments will depend highly on the accelerator parameters like flops, memory, connectivity, as well as the microarchitectural details. If we pick a new set of parameters to start with, the infrastructure stack adapts and we're back to 20% utilization, but for different reasons. If we're just going to revert to the same utilization given any new chip due to the inefficiencies in the rest of the infrastructure stack, it means that things like individual chip peak performance do not matter much. What does matter still is system performance per dollar, and that is of course still connected to chip performance per dollar. I see a lot of emphasis on designing powerful new chips, but I think more exciting opportunities lie in thinking about the design of whole systems from data center down. So, if we design a warehouse scale size system, as a computer runs machine learning programs? What are the great ideas that apply? Are they the same as the classic ideas in design of regular computers? System engineers such as myself have taken random subsets of ideas from computer architecture and built software systems around them. And is this really the best way forward? I think the opportunity lies in integration of communities such as chip designers, system software engineers, language experts, and machine learning researchers to co-design the warehouse-scale hardware systems of tomorrow. So the second opportunity is with us truly embracing the fact that we've reached a point where there really isn't that much more room left at the bottom. Of course, I'm referencing the brilliant lecture Richard Feynman gave in 1959. What happens to our giant warehouse-scale computers when we've reached the bottom? I'm going to take a bit of inspiration from how Richard Feynman thought about these things and suggest we think about them from first, most fundamental principles. So, what actually matters for these tiny computers? There really are only three absolutely necessary ingredients: silicon, power, and software, or at least maybe until quantum computing comes around. As a thought exercise, how far are we in terms of theoretical performance per dollar from today's systems if we were to build a minimalist system from first principles? Let's just look at basic materials and discount non-recurring and operational costs for now. So, just looking at silicon, the floor of the cost of an instruction is around 3 orders of magnitude lower than where we are now. For power, surprisingly, we can still look at silicon. Sunlight is abundant, and while you can't build low latency services powered by sun due to nocturnal habits of humans, high throughput machines for research might work just fine. Here we also see about a 3 orders of magnitude difference. Of course, this is just the basic material. I've not accounted for manufacturing overheads, wires, packaging, structure, operations, etc. However, there are 2 trends to watch out for. So, the first one is that components keep disappearing into the silicon. First it was the wires, then all leftover circuit elements, power electronics, optical transceivers, and even support structure are all slowly disappearing into the silicon. And second trend, of course, is that we keep making more computers and thus more silicon. So to bridge the gap, we can accelerate these trends. First, we should look to take advantage of moving everything into silicon that is not already there. And we should do that even if the solutions look to be a lot more expensive. This would force us to build systems out of components that are only absolutely necessary. And finally, we should exploit nonlinearities of various system properties with respect to scale. These are not obvious. For example, weight of computer systems has nonlinear effects. There are various step functions of how hard it is to handle modules, machines, and racks with respect to their weight, because of things like humans getting RSI from handling heavy equipment. I believe that designing systems like this by starting from principles and exploiting nonlinearities in physical and system properties will be a paradigm shift. I don't know for sure, but I think this implies that systems composed of few complex, expensive, and reliable components would be replaced by an ocean of smaller, simpler, less reliable components. If you think this is impossible, we've seen this kind of paradigm shift before. Data centers used to be just a collection of individual machines, and Google changed it all, starting with then a ridiculous notion of corkboard motherboards rack with a floor-standing fan next to it. We take for granted that data centers nowadays are gigawatt-sized systems that are meticulously designed for whole system efficiency, but it was not always so. Finally, we should think about economies of scale. 20 years ago, solar power used to be only of interest to NASA and university departments. But now, it's unthinkable to build a new house without solar panels. The fast pace of process node improvements and the high cost of fabs has prevented the community from looking into scaling up production. Moving everything into silicon, including structure and scaling up production massively, should be possible now that Moore's law has slowed down. And so I believe we need a gigafactory moment for compute. So we talked about silicon and power, but what about the software floor? What can the software look like if we deconstructed down to the first principles, and is there an opportunity there? By Y2K, we learned how to run collections of distributed services over thousands of commodity machines. Gradually, machine learning has caught up to this complexity. Modern machine learning systems, especially the kinds of AI agents that are built at DeepMind, are really collections of distributed services. And to accommodate this, the infrastructure we rely on had to massively increase in complexity. In our investigations of where our biggest gains in performance per dollar come from, we have noticed that we get the biggest gains from paradigm shifts in the chip or system designs. The process node improvements are just the wave we all ride on, but truly big changes come from creating very different looking systems. We'd like to see more big changes like this, but there's a problem. Due to the size and complexity of the software stack, we have seen the gains from paradigm shifts just dissipate. Our infrastructure is just not able to take advantage of new system designs fast enough that potentially would now expose different bottlenecks in the rest of the system. Another reason we need more paradigm shifts in hardware systems is that having diversity of hardware is good for AI research. Researchers adapt their work and, to some extent, their thinking to fit within the constraints of the machine. We believe that it is essential for us as a research institute with a very long-term goal to do our work on a variety of hardware platforms. But once again, the software infrastructure at all levels is not flexible enough to adapt to the variety without creating a lot of friction for the researchers using the systems. So we see this every time we try to use a new accelerator. For example, it takes a long time to make it generally usable. The high software overheads also inadvertently cause us to overinvest into existing platforms to minimize risk. But perhaps this time it can be different. AI programs are a lot more constrained than general purpose client-facing services. They have a highly regular macro structure. They're mostly throughput-oriented and constrained by raw arithmetic performance. There's quite a lot of low amount of any kind of data-dependent control flow, and most importantly, the timescales for straight-line basic blocks are in the same order of magnitude as communication latency within a data center. Such should allow for software-based control of the whole distributed programs. So we have been talking about data center as a computer for a while now, but perhaps we could start treating our machine learning experiments such as a program that we run on such a computer, instead of treating them as a collection of programs running on a set of communicating computers. I believe there's an opportunity to go back and look at systems and programming languages research from the 70s to the 90s and redo some of this in this new context. So compiler friction and inflexibility is one of the biggest issues preventing quick adoption of new systems. Is there an opportunity to rethink how we build compilers, given the recent advances in ML? Trivializing this a bit, compilation and program optimization is about making good choices for program transformations, and traditionally is done with a lot of human knowledge baked into the code. This is no different than what we do in the rest of the stack. We add one special case and heuristic on top of another to make our tests pass and meet performance targets. However, nowadays we're very good at learning how to make good choices and model complex systems. Could we use these new tools to build compilers and eventually the rest of the infrastructure stack that are more adaptable? This would allow us to radically slim down the code base. Only few specialized pieces would remain, with the decision engine and optimizer shared across many such problems. More adaptable compilers would allow us to take advantage of diversity of hardware and any paradigm shifts. Even if the overall performance of the output is lower in benchmarks, so due to our low overall utilization of whole systems across research programs and the great benefits from paradigm shifts, I believe we still have a big net positive. Of course, this idea is not new. This is what is often referred to as the quote-unquote magical compiler, which is considered impossible. However, I believe I am going to be on the side of history, which is littered with the corpses of systems that believed that deep learning would never be able to replace them. In 2010, speech recognition had a complex pipeline, and it got replaced by a deep net. In 2012, computer vision also had a handcrafted pipeline, which got replaced by deep net. In 2014, machine translation similarly had a very complex training pipeline, which once again got replaced by DeepNet. It is now 2020, and compilers and many other components of modern systems infrastructure stack have lots of handcrafted parts. What will they get replaced by? Perhaps it will be a deep RL agent. So, in conclusion then, I remain very optimistic about the future. Output from AI research have the capability of making our world a better place. To achieve that, we need to bridge the gap between demand and cost of compute. We have at least three major opportunities to do so. First, we should consider the whole systems from top down and look at what many years of computer architecture research can teach us for their design. Second, we should fully take advantage of economies of scale. More of simpler and cheaper things trump smaller and more exquisite things when scale can be leveraged. Just like in machine learning, it is a bitter lesson for any designer. Third, we should re-examine how software should be built in an age of powerful decision engines. Optimizing for usability and flexibility at the cost of short-term performance loss will bring us long-term benefits by unlocking more paradigm shifts in computer systems. All right, thanks for listening, and I look forward to your questions.
Let's thank Dan virtually through Slack, and I will golf clap politely. That was an awesome talk, Dan. I really loved that. We have a number of questions on Slack. Please keep on asking things in Slack, and if we're lucky, we'll also have more participation by Dan on Slack after the live period has ended. We have about 10 minutes left. Our first question up comes from Eric Swan. Do you believe it's possible that an algorithmic breakthrough will make AGI possible on current digital hardware architectures, or do you believe new hardware architectures are necessary for achieving AGI?
Can you hear me all right?
Yep, hear you great.
Great. Thanks, Eric, for asking this question. I think the honest answer is that I don't really know. I don't think anyone really knows, but at least from a theoretical perspective, the machines we have should be complete enough. And I personally hope that we can get to a sort of general intelligence that is widely useful with silicon in some form, right? We won't have to invent a completely new medium of computing. But to be honest, I suspect machine learning research luminaries in the field, they probably have a better answer than I do about this.
We have a related follow-up question from Xin Wang. Big starts from small, with more focus on whole system design. What fundamental component level hardware and software changes to enable deep RL might happen in the next few years? Could you please mention top items in your mind? And maybe I'll give you a hint here. I feel like you were the one who told me about DeepMind's neurologically inspired approach to things and how brains have structure. So maybe there are brain structures that DeepMind researchers and others have used to inspire mechanisms that we build in deep learning?
Thanks for the question. I mean, it's a little difficult to answer because I'm not sure, at least microarchitecturally, there will be many changes that will suddenly unlock a AGI or something like this. But I mean, perhaps one thing that we haven't really looked into from a computer architecture standpoint is things like accelerators that help with memory systems. So, for example, if you look at papers like Never Give Up, where they use a KNN based memory to improve performance of various agents. We don't really have any hardware that accelerates this. So that could be an interesting area to look into in the future.
Maybe I'm editorializing a little bit, but exactly about memory. I think that DeepMind's own neural Turing machines have a memory-like component to it that's reflecting brain structure, and that the attention mechanisms are relatives of neural Turing machines that are powering transformers and BERT these days. So I feel like some of the architectural structure we might build in our computers could follow some of the brain structure that is out there in biology.
Agreed.
Okay, let me ask a paired set of questions. Xin Wang also asks, how much faster is RL prediction compared to simulation in your fluid example? And in a related question, Ashish Maurya asks, it's very impressive that the physical interactions of particles being predicted are as good as simulation from actual physical laws. Can this approach work for physical interactions like ray tracing as well?
Honestly, I don't remember offhand what was mentioned in the paper. So I do have a link, I think, on Slack now to the paper, so you should all take a look. But in my conversations with my colleagues, right, there could be multiple reasons why these simulations eventually, or machine learning based simulations eventually, would be much faster. And I think the primary reason there is that we integrate a lot more information with every step, and so in theory we should be able to modulate, you know, both the time scales as well as the coarseness of the actual mesh or the number of particles in the simulation, perhaps dynamically also in the future. And so it should be possible to basically automatically adjust the step that we take such that the simulations we actually do will be much faster. And the other thing I think that will help our simulations go faster is that we have models, there are many models out there now where you can effectively sample configurations. And so they give us a way to basically sample from a distribution that is not sort of infinitely meaningless, right? You will actually get samples that actually mean something useful. So maybe that answers the first part of the question. And the second part about this being useful for ray tracing or generating structures, I don't know of any case where we've done it internally, but I remember seeing several papers at least where people generate in-game structures like chairs and rooms and things like this. And also there are several papers where people have written differentiable ray tracers and also physics simulators that can be used in conjunction with machine learning.
I think Iole Mokagata is playing hardball, and he asks, or they ask, can you highlight the top 3 problems that RL has helped to solve and whose solution has been life-changing?
I mean, life-changing, I think, is an interesting bar, right? Like, it might be different for different people. But of the big problems that we have solved with RL, that I'm aware of, at least, right? I think our understanding in the solution of Go, chess, shogi at superhuman levels, those were quite significant milestones. And I think we've also used RL for control problems. So there are problems that have been solved only with reinforcement learning in robotics, in control of building systems like data center cooling. I know people have used RL also for controlling sort of more low-level systems, like if I remember this, there's some work on coordinating braking on trains to save energy and things like this. So, those would be kind of examples that come to mind.
Our next question is from Dave Patterson. Do you think MLPerf benchmarks are good targets for computer architects to target? And maybe I'll personally pile on a little bit and say MLPerf has had a tough time figuring out how to add RL benchmarks into the suite because RL is a little bit squishy as far as the accuracy metric and performance metric you should use. So maybe general commentary about MLPerf and how MLPerf might better match DeepMind and what it wants to do.
Dave always asks the hard questions, doesn't he? I think MLPerf is great because it gives a sort of a general yardstick in some direction, right? Like we can tell something about the accelerator system if they've participated in MLPerf. But the difficulty with RL, and I think maybe more broadly, the difficulty with research is that we don't want to know necessarily how fast one thing runs. We would like to know how fast everything runs, even the things that we haven't written yet. And so in that sense, it's, we've also struggled with how do we add those kinds of requirements as a benchmark into MLPerf? How can we help you? And so I'd say usually when we think about new systems, we try to think about sort of a phase space of performance, right? If you vary parameters, how does the performance of various computations changes to give us an intuitive feel for how well the system would perform. So I don't think any one benchmark is sort of is going to be good enough. And unrealistically, it would be nice to do basically a search across many architectures of different depth, of different width, of different structures in them, that would give us like humans, an intuitive feel for how these systems work. But I think, from a practical standpoint, it would be very prohibitive. So I think MLPerf, as it is now, has picked a nice sweet spot where people can participate and they don't have to spend years writing software. So, but perhaps once we solve the software problem, these things will be much easier to do. So that's what I'm hoping for in the next, let's say, couple of years.
And then once we solve the AGI problem, we can solve all the other problems.
Yeah.
Next question is from Christos Kozakis. Any thoughts on the increasing amount of work on using ML for systems to overcome some of the design and software problems you're talking about?
I think ML for systems is great. I would like to see more of it. It's like with any intersections between fields. I think it's difficult. It's difficult to convince people that this is worth it. It's difficult to find people who can do it on sort of both sides, right? I don't think all systems people necessarily see the value of this, and not all machine learning people see what's interesting about it. My wish is that in more computer science departments, people wouldn't specialize too early, but would have the ability to basically do this joint work that would target multiple domains at once. So maybe it's computer architecture and machine learning, or simulations and machine learning, or systems and machine learning, etc. So I guess the common theme is machine learning, because I think it really is like super powerful tool that we all should get used to using and thinking about, just like maybe 20, 30 years ago, it was common to say like programming would be this super powerful tool that everybody should really learn how to use, no matter what profession you were in.
I think we have time for one last question. So Ian Cuttress asks, does using ML to create and optimize a special universal compiler result in the problem of not knowing how it goes internally? Wouldn't this lead to issues where rogue compilation or a biased compiler goes unnoticed?
Sorry, Cliff, could you repeat the last part of your question? I couldn't hear it.
Right. If you used ML to build a special universal compiler, are there issues about whether rogue compilation or a biased compiler might go unnoticed because of difficulties in explaining what goes on inside of our ML systems?
I think it depends on how we build it, right? Building any systems that translate without also thinking about some form of verification, and those would be for systems that we would actually rely on, I think is not the right way forward, right? So if we're going to build this magical compiler, we have to also do some work on verification. So every transformation that the compiler would pick has to be correctness preserving in some ways. Otherwise, it just doesn't work. So I think the difficulty is, what are those transformations? What are the abstractions that we see at multiple levels? But we certainly cannot sacrifice correctness. So in that sense, maybe it's a little bit different than the super compilation work that was done 10, 20 years ago.
Okay. Dan, thank you so very much for this talk, which I think expanded our minds and showed us different vistas about this area, which is clearly important to and infiltrating many aspects of our community. But seeing the view from the scientific forefront has been huge for us. So please join me on Slack in thanking Dan once again, and continue the dialogue with him there.